Okay. C and D vary with constant rate of change. Is D proportional to C? It might be. Okay? Not necessarily. That's not the heart of the matter, right? So it might be, but not necessarily. If you said yes, well, yes is wrong. No, the whole point is that's not what constant rate of change is about. Explain, what is constant rate of change about? What's proportional? Changes are proportional. Changes are proportional. You get it? Yeah. So, yeah, if you put no, that's a lot closer than yes. Yes is not right. Okay? So, changes are proportional. So, therefore, if C is independent, D is dependent, delta D equals? K delta C. All right? How is the constant rate computed? We said delta D over delta C. Some nods. That's it. Explained with one sentence is, it's the changes in D and C that are proportional. D and C might be proportional, but the key is it's constant rate of change. The changes must be proportional. Okay. Okay, let's review it again. It's going to be everything for us, okay? That's why we're really working hard. So it's like the back of our hand that we understand what this is about. Because it's kind of, when things get complicated and hairy, this is kind of the bedrock. This is what it's all based on, okay? So, two quantities, this is what we said. Two quantities x and y change together such that changes in one quantity are proportional to changes in the other. All right, so what does that mean for every change in y? K times change in x, right? If you're going 62 miles per hour down the highway, changes in distance are always 62 times changes in time, right? You take the change in time, you multiply it by 62, it gives you the change in distance. Okay, similarly, every change in y has the same size relative to its corresponding change in x, and that relative size is the constant rate. That's the constant rate.
Are you recording?
I'm recording, thank you. Okay, so that's review, and this is hopefully getting burned in our brain. Okay, so accumulation. So now we're starting to talk about accumulation, okay? Accumulation, so the first blanks are, one of them is input, one of them is output. So when we track accumulation of a function, are we tracking the accumulation of output values or input values? Output, okay, so output, or we also call that generically y values, right? Okay, so we're tracking, we're looking at a function, we're looking at accumulation, we're tracking how the output accumulates. And accumulation can be recession too. So accumulation, it kind of has a connotation of building. Okay, but accumulation, the way we talk about accumulation, it could be a building accumulation or receding, right? Decreasing is still accumulation under the umbrella of accumulation. Okay, so we track how the output accumulates as the input changes, right? Okay, so therefore a bit of accumulation, how can we represent a small bit of accumulation? Small change in input, so we're going to take a change in input. Is that a change in input will give us a small bit of accumulation? Agree? What would represent a small bit of accumulation? You just told me accumulation tracks what?
So it's output.
Output, y values. So what's a small bit of accumulation? Change in y, change in y. Change in y is an increase in or a decrease in the y value, right? So that's a small bit of accumulation. And with constant rate of change, how can we compute delta y?
Delta x.
Nicholas wants k delta x. What do you think?
Yep.
That's it. That's what I've been talking about. So the whole point, or one of the major points while we were hammering about constant rate of change is this principle will help us find small bits of accumulation. For if we have a constant rate for a small change in x, we can easily calculate the corresponding amount of accumulation in that small change of x. Like for the next two or 3 weeks, like this is kind of has to be the centerpiece of everything. This is the big idea, right? This is the big idea. We're going to get lots of nitty gritty. You can't lose the focus of the big idea. Is that we're tracking the change in y, the accumulation of y. Little bits of accumulation are delta y, and if we have constant rate of change, we can calculate those by k delta x. You see? Really important. Okay, so here's our tax due, and here's showing a current value of tax at 58,000. So current, right here, this is the current value of, not tax, sorry, income, taxable income. And we've seen this before, we know how this works. So we can represent the tax due on 58,000 two different ways. We can represent it as a whole amount, like a taxable, just a one lump sum amount. You come to the end of the year, you open up the tax table, you find in the table how much you owe on 58,000, right? So we can represent it as an amount due. Or we can represent that amount of tax as the accumulation of tax over the whole year. That tax grew little by little by little until it got to the final amount. So see if you can do this. So given these, so we got the tax rate function there, and we got the tax function here. How can you symbolically represent? I'm not asking you to calculate a value. I'm saying how can you symbolically represent the tax due on 58,000 as a total amount of tax and as an accumulation of small amounts of tax? Take 30 seconds and see what you come up with. So we're just representing. We're not calculating the value. So we want to represent it two different ways. Okay, let's see what ideas you have here. So Danny. No. Juicy. Could you represent the tax due as a total amount of tax? What would it be? How could we represent that amount, the amount of tax you owe on 58,000 as a total amount of tax? Do you know? Sean?
It would be the area under the graph to the right.
What does area have to do with taxes?
No.
So here, watch out. If you've had calculus before, do not anticipate where we're going. So, and this is fair, okay? He's had calc before. Area has nothing to do with taxes. So we're not touching area because it has nothing to do with taxes. Okay? I know that that's what you were taught, but we got to unlearn it quick. If you think we're going towards area, unlearn it. Forget it. We're not talking about area because area has nothing to do with taxes. Okay? All right. So no, I'm glad you brought that up. How can we represent the total amount of tax? Anybody? Peter.
The y value of the point at 58,000.
Which? So I got 2 points. Which point?
Graph on the right.
Graph on the right. So how do I represent the y value? How do I represent it?
Draw a line over to the y-axis.
No, I want to write something that gives me the total amount that represents the total amount of tax.
F of 58,000.
And what is it called? It's not called F. What's it called?
X. R of 58,000.
What's the name of the function? Tax. Tax of 58,000. All right, tax of, right, output. That's why we went over function notation, right? Because we can represent numbers without actually having the values. What is that? That expression right there means how much tax you owe on 58,000. So what about this accumulation of small amounts of tax? Yeah, Christian.
It could be tax
Okay.
I said 0.25 times x minus 58,000 plus the tax of 38,000.
Okay, no, small amounts. So you're kind of taking them in these big brackets. So we're thinking about accumulation now. Accumulation is bit by bit. Chloe.
Do you want to draw something on the graph to show it? Instead of like-
No, I want to write an expression.
Okay.
Okay.
So
Janae.
y1 plus y2 plus y3.
Y1 plus y2 plus y3. What do you think?
delta y1.
Or you want delta? Should it be y1 or delta y's?
What would delta be?
And how many am I adding together?
58,000.
All right, if we're going to do $1 of income at a time, we'll have 58. So the question is, are we adding together y values or are we adding together delta y's?
Y values.
Think of it. What does the y values mean on this graph? What do the y values mean? Is that the tax on that dollar, or is that all the tax up to that many dollars? That's all the tax, right? So if I do y of 40,000, that's all the tax you owe. That's a lump sum. That's like this, right? So this is a y value. So how do we accumulate? Yeah.
So could you put tax of, or whatever the value would be, like 83, or whatever the value is when they change, and then you could do the next interval minus the tax of the 8,300 or whatever.
Yeah, you could do that, but it's like kind of way overcomplicating it. How instead can we get the little amount of tax on the first dollar?
Delta y.
Delta y, right? And how can we get the little amount of tax on the second dollar? Yeah, so that's, you're subtracting. You're going ahead and expanding all those out. And we could just write it as delta. So yeah, what you said is okay, but it's just not the simplest. So you see, these are the same thing. The tax you make on the first dollar, the tax you make on the second, the tax you make on the third. If you add those all up, all the way up to 58,000, it's the same as the y value of that graph, right? The total amount of tax. Representation is everything. When you read all these mathematical symbols, you got to know what you're looking at. So that's why we're practicing representing these quantities. Okay? Okay, so, and what are our y's? They're delta tax. So you can do it this way as delta tax 1, delta tax 2, or summing up the delta y's. Really important principle here. Two ways to get the same amount of tax. As an accumulated amount, little bit by bit by bit, or as the value of the tax function at the current amount, 58,000. Okay, questions on that? Okay, so this is not very, we don't want to write this out, right? We keep writing the same thing over and over again. So we have a notation that helps us save time and save writing. Okay, so really we would just want one of these. They're all the same. They're all delta y. So we can just, all that changes is like the index, which delta y it is. So this subscript is just telling us which delta y it is. So we have this symbol that means sum a bunch of these things up as that thing changes. So our starting value of I is what? 1. And our final value of I is? 58,000. So K, again, K means 1,000. Okay, so that right there, that notation is the same exact thing as this right here. Those are exactly equal. It's just, we don't want to sit here and write this. We're writing the same thing over and over again, right? So why not just write it once and have some notation that means this repetitive addition? Okay, so this is Greek sigma, and so you can remember sigma because it's sum. So we're focusing on accumulation because we're looking at accumulation in bits, right? Bit by bit by bit accumulation. So we're going to see this a lot. We're going to see the summation notation. So let's practice. Let's practice the summation notation. Do the symbols make sense? It means sum up a bunch of delta y's where the first one is the first, delta y 1, and then all the way up to count by integers, by whole numbers, up to the 58,000th. So that's going to add 58,000 things together. Do you see that? Okay, so see if you can write summation notation for that sum right there. Can you do it? So I'll start you off here. So what do you need? You need starting, ending, and then what is it you're summing together? What is it you're summing together? So starting value of I, ending value of I, and then what kind of thing? So this can be any expression that has to do with I. So what is it you're adding together? So what's the starting value? That's easy. Finishing value? So now the question is, what are we? Is it yi that we're adding together? What are we adding together? Aaron? Change in I. So what's the first thing we want?
Every previous one.
Yeah, it's just I, right? We're just adding up whatever the value of I is, right? The first, when I is 1, we want 1. When on the second one, we want 2. Yeah.
Do you want us to use the variable I?
Yeah, that's just a common one. It's like using X for input, but it's not required. Yeah.
I have a question.
Yeah.
With that expression though, isn't that saying 1 plus 2 plus
Yes.
so
And that's what it is. 1 plus 2 plus 3.
okay, so that sigma saying it's gonna add everything parts of that, right?
It's going to add up 100 things.
Uh,
The first thing is going to be when I is 1, so it's going to be 1. The second thing it's going to be is when I is 2, it's going to be 2. You see?
so the answer's gonna be 3 then. I wanna know.
No, it's going to be the sum of all the numbers from 1 to 100. It's going to be this expression. So these are exactly identical. Does that make sense?
Yep.
Okay, so now here. So now can you write out what this means? So we're going to go backwards now. So you're given, I'll write it bigger, it's kind of small. So you got, this says I equals 1 to 90, I squared. So now I want you to interpret that. What sum will you get when you do that? Go. So when you do that, what sum will you get?
Like the actual answer, or just write it out?
If you can get the actual answer, I'll give you an A in the course. So it's always about representation. Yeah, right. Type what in a calculator? You need to have a calculator that does that, which exists, right? Okay, so graphing calculator will do this easily. Okay, what's the first term? And how did you get that? 1 comes from what?
I. Bottom.
1 squared. Then next term. 4. 2 squared. How long will I do this for? What's my last term? Making sense? So we're just practicing the notation. Do you see how the blue things are equal? That is the same thing as this. Okay, write out this one. Can you read it? Is it big enough?
No.
No problem. I equals 1 to n r sub I delta x. Same thing, interpret that. What is that saying to do? Write an expression that describes or is equivalent to that. Compare with the person next to you.
This is 1 delta x plus R2 delta x plus R3 delta x all the way up to n.
Shayna.
I don't have to get
Oh, I'm supposed to see this?
No, but then I like whispered at you. Heard me.
I don't want to be rude. What if we want a different kind of increment?
You build that into the. You always will increment by 1. You want to build that into your expression so that whatever you're doing makes it skip by. Right. So if you had some expression of 2i in here, that 2i would be going by 2.
Oh,
You see, so you don't do it here. You do it in your expression.
So I think it's
Okay, Shayna, you're up.
Oh, I am.
So what is this going to be?
I put like R1 delta x and R2 delta x.
She wants
All the way to R.
multiply together r1 delta x times r2 delta x plus r1 delta x plus r2 delta x plus r3 delta x. The last one will be rn delta x. That's it. All right. What might this be referring to? So why this example? What might this be? Adding what?
Like gradual distribution, so the accumulates a small amount to place without changes.
Because why would this be accumulation of small amounts?
Because it's like we do this.
Right? Rates of change
Multiplied by the change in x.
gives you what?
Changes the total change, right?
What could each of these represent? Delta y's, right? Delta y1, delta y2. So now we're using that summation, n. So we see how this kind of comes into play. Adding up a bunch of delta y's, right? If you have constant rate of change on each interval of x, then that delta y can be calculated as the rate times delta x, the rate times delta x. Okay? Here's another way to do it. So what are y values? Y values are, so what kind of function is the f function? If we're talking about the same thing then. What kind of function is the f function? So what kind of output does the f give? A y value that we're accumulating?
it's a rate.
Gilbert?
It's a rate.
Why? Why do you think it's the rate?
Because it's being multiplied by the change in x.
Yeah, right? Y is k delta x. So in this example, what it looks like, we can kind of assume that the f function is, this is a rate function, right? This is a rate function. So we're looking rate times delta x, rate times delta x. So what do we have here? I equals 1 to what? Let's do j. So Chloe wants to do something different. That's great. J equals what? 1 to k. And each term is f of x j times, again, summing up little bits of accumulation. Our rate function is this f function, is the rate times delta x, right? And then we're summing up a bunch of little delta y's. Okay, does the notation, the sigma notation, does it make sense? Oh, hey, look at that, J and K. All right, so you did some of this for homework, right? So I have a basketball. It's rocket powered. Okay, so every half second a rocket fires off and it changes something relative to how this basketball is traveling through space. So I want you to make sense of this animation. Take 1 minute, talk to the person next to you. Make sense of everything you can in this animation, okay? Talk about what you're seeing here. What are you seeing?
I didn't know this is when I use the box, right? Function.
So we're just making so anytime you walk in the balls have took physics in this ball.
Okay, let's see how you did. Where should you look to see the elapsed time growing? Where should you look to see elapsed time growing? Jonathan.
The x-axis on the left.
The x-axis on the left. Does that show where the time is growing? Yeah, so this is number of seconds, and the length of the black bar there, as it extends, is the number of seconds. Okay, so that's right. Okay, where should you look to see the basketball's velocity for the current value of elapsed time? Where should you look, Austin?
The y-axis of the left graph.
The y-axis of the left graph. You agree? So we come along here and boom, paused. What's the current number of seconds? 3.2, 3.3. And what's the velocity of the ball? 6 feet per second at this current value of time. Make sense? Where should you look to see the basketball's height for the current value of elapsed time? Yeah, so I'm helping you out a lot here, right? There's the ball, so it's the which axis? Y-axis of the right graph, okay? Current value. The current value of the basketball's height is if we pause time, right? The ball will be somewhere. So that's the current value of it. So whatever its height above the ground is when we pause time, for instance, boom, I just paused time at 4.9 seconds. So the current value of the height, you estimate is? Yeah, 21, 22, something like that. That's the current value of the height for a current value of time. Okay, so what does a point on the left-hand graph represent? What does that point represent? Somebody new? Let's see. Who's up? Mackenzie, you're up. What does a point on the left graph represent?
A point is the number of seconds per velocity.
So number of seconds. So are you trying to make it into one thing, or is it two different things?
Well, I mean, it's two different things, but it's the number of seconds, like according to, or not according to, but with the feet per second.
Right. Yeah. So it's a velocity, and at the current time, right? So it's that point. The x-coordinate is the current time, and the y-coordinate is the velocity at that point. So is this an accumulation function or a rate function? And what kind of rate function is it? Is it constant rate? Is it changing rate? So is it a constant rate of change or a changing rate of change? This rate graph. Gilbert said both. Why?
Because it's constant in certain brackets,
Okay.
but it's changing over time.
Okay. What were you gonna say, Clay? Right. So how can we talk about what that is? So it's both constant and changing, right? So we call that what? Yes, a piecewise constant rate of change function. For each half second, the rate is constant, and then at the end of that interval, what happens? How does it change? How does the rate change?
Increases.
Increases. How does it increase?
By
Abruptly, right? Suddenly changes, right? So we got a constant rate, then suddenly changes to the next higher constant rate. Then suddenly changes to the next higher constant rate. So we got a constant rate of change piecewise function. Okay? Is it realistic? Is that how when you fire a rocket or fire something in the air, is that what velocity does?
No.
Christian?
My question is, what's it called? Does that mean if we let this kind of go on for long enough, would it also start to like decrease in velocity when, like, let's say the rocket was like out of, you know what I mean?
Okay, so yeah, we're not talking about any of that. So I'm just modeling it just like this. Every half second, what happens? The rate jumps to a constant rate that was 1 feet per second greater than the one that was before. So is that a realistic scenario, Aaron?
That's not realistic because it's a sudden jump, it's not a gradual increase.
Right, okay. Yeah, so it's not realistic. Although there were bombs in World War II called buzz bombs that had these rockets on them, and so every time you fired a rocket, it would burst at a higher speed. So it's something like that. It's something like that. But this idea of a perfect constant rate and then suddenly a perfectly faster constant rate is kind of unrealistic. But for us, at this point, it's what we need. All right. So it's we'll see why later why we're using this, but because we like constant rate of change, we understand the mathematics of it. Okay. So we're going to model this basketball as abrupt changes in rate, but then within intervals, constant rate. Okay, so in what ways does the basketball height accumulate? How does the basketball's height accumulate? Oops. Sorry. All right, so we'll just go on from that. So that's what we're talking about anyway. Any questions on what you're seeing here? What the scenario is? We've got a constant rate of change, piecewise function that's showing us the velocity of the basketball, or this theoretical way the velocity of the basketball is changing. Okay, so what would happen if we now let time, so what I'm going to do now is, now we're going to graph over here the accumulated height. So now over here I'm going to let also the number of seconds increase on the right graph, and we're going to graph a function of the height as a function of number of seconds for that rate of change graph. So I want you to talk for a minute. What will you see? So what I'm going to do is instead of having the ball go right up like that, well, it'll still keep going up, but we're going to let time increase here. And we're going to graph feet from the ground as a function of number of seconds. What will you see over here? So talk to the person next to you. What will you see? Got your idea? Got your idea in your head? Here we go. Is that what you thought? Is it a curve?
Yes.
People are saying yes, it's a curve. Is it a curve?
Yes.
One person saying no. Anyone says no? Is it a curve?
No.
Why not?
Piecewise.
Nicholas?
It's like a piecewise function.
It looks like a piecewise function. Is it a piecewise function?
Yes.
we have a constant rate of change piecewise function, like that, with these constant rates, what kind of accumulation do we get? What is it? Piecewise what?
Accumulation.
Yeah, piecewise pieces of lines, right? So that's what you were doing with the tax function. That's what we did with the tax function. Okay, so and you should be able to write the piecewise function for this. So see if you can start. All right, so quick.
How many?
So what's happening over here is, let me turn that thing off. I think it's this one. Yes. No, wrong one. Maybe it's this one. That's it. That's the one.
Do we count for 0?
There we go. Cool. All right. Write the function for this. So what do you got? Every half second, the constant rate increases by 1 feet per second. Every half second, the constant rate increases by 1 feet per second. So can you write this function? Just not the whole thing, obviously. Maybe just 3 or 4 pieces. Yeah.
So this is just a question about how to make it more concise. Supposing that this went on for like infinity, always increasing, and you wanted us to write the function, is there a better way to write it to like show that every time it increases by 1.5?
Yes. That's where we're getting. That's going to take us a week or 2.
Okay, so
Yeah. No, totally. That's the right question, right? So can we do it in one? Can we do these multiple lines in one line?
Yes.
Yes. Cool.
Is that what the homework was asking in 17?
Not yet. Okay, work on this. Quick, we got some more to do, so see if we can do this. I'm not sure why. What happened to the ball? Oh, there we go. Okay, that makes sense.
Maybe it's 0, it's just x. Maybe it's 0, it's just x. Here's the
So if you want, you can call
No.
it h of x for height. Hopefully you started with one of those. Each piece will be, what will the general form be?
Points there.
Right. What is it? Brent, what will the general form of each piece be?
KX.
Kx? All of them will be Kx, like that?
No, it'd be like
No.
your rate times x minus 2.
Yep, we need the point slope form, right? Is that it? Plus b. Each one will be one of those. And how will we get each b?
Or y or h.
Yep, it'll be h of where we left off before, right? It'll be the height that we left off at the end of the last interval. Okay, so in the first interval, what's the height? What's the rate? The rate is 0, so it'd be 0 times x minus 0 plus 0, that's all 0. So if you just put 0 there, you were right, and that's from when to when?
0.5.
Okay, next one. The new rate is 1. Plus h of 0.5. And that's over the interval? 5 to x to 1. Got to know how to do this for your quiz, okay? This is your quiz this week. I put, actually, in the quiz and exam area, I put 3 bullet points of what you need to understand to succeed on this quiz this week. But this is the kind of thing that it is, okay? one of the things. This is one of the things on the quiz. Read the bullet points. Okay. Next one will be, what's the next constant rate? 2 over what interval? So it'll be x minus 1 plus the height that we got in the first second, right? From 1 to 1.5. Sorry, that should be less than, strictly less than. Okay, does that make sense? Is it a curve? Not a curve. Why isn't it a curve?
Seems abrupt changes.
Right, because the rate stays constant, and then suddenly the rate changes, and then suddenly the rate changes again. So at a constant rate, our accumulation is linear, right? So at constant rate of change, accumulation is linear. Okay. Anybody have a question about that? Cool. So back to this. The right place? Here. Okay, so let's talk about accumulation. So say starting here at 2 seconds. So we know this is not a curve, right? This is not a curve. It's a bunch of little lines. Each line is 1/2 second wide, right? So starting here at 2, how can I get a little bit of accumulated height? First of all, how can I represent 1/2 second starting here at time equals 2? How can I represent 1/2 second going by? What's that? H of 1.5. Will that show us 1/2 second going by? What can I do to show 1/2 second going by?
Would be H of 2.5.
I want to show, so now I'm not asking for an expression, I'm asking to show, how can I show?
You're showing a horizontal.
How long? Yeah.
Horizontal change.
Of?
0.5.
All right, so right there, that's like a little delta x of 0.5. How can I show the associated change in the height? How can I show it? Show it on the graph. Yeah, so there's going to be an associated, right there, an associated change in y to that change in x. How can I compute that associated change in height? Anybody? What will it be?
K times 0.5.
He wants k times 0.5. So you're doing k times delta x? And what is k? What's that? Ross, did you say? Oh. 4. Why 4?
The graph on the left, you can see
Look at the graph.
rate's gonna
The rate is,
be 2.5.
over that 1/2 second, the rate is 4. Or that's what we can call these, like these are the velocities. This is the velocity at 1, 2, 3, 4. This is like the 5th velocity, okay? So k is 4 delta x. And what is delta x? So what is the change of the little accumulated amount of height in this 1/2 second? 2. You see? Right now, the rate of change is 4. So if we go 1/2 second, we'll get a little change in height of 2. All right, what about the next one? So another change in x. How can I get that associated change in y? What is it? 5. She wants 5 delta x. What do you think?
Yep.
What will that be? 2.5. So every delta x I go 1/2 second, I've got constant rate of change, so I can just apply constant rate of change to get the associated little change in y all the way here. So that's what's being shown over to the right as well. Okay, so each one of these, so say this one right here, I don't know, let's see, so this one right here is being shown by the change in height from there to there. And this one Right there, the change in height from there to there. So all those velocities, those are our k's. Those are our constant rates of change. And we can get each one of these. So V5, that's what you said was 4. So V5 delta x, V6 delta x, V7. Okay, I went one too far. So how can we get the total accumulation of height? So V11 is up to, what is that, 5.5 seconds? How can we calculate the total, the height above the ground as an accumulated amount in the first 5.5 seconds? How can we represent that?
Sigma notation.
Okay, which does what?
It sums them all.
Sums what? What are you summing?
P for V values times delta X values.
So you want to sum these up here?
So what is V then?
What's that?
Saying you can pick any of them, so it would be
Okay, so let me rephrase the question. How can we calculate the accumulated height after 5.5 seconds as representing it as an accumulated amount? I'm going to start with V1 delta x and do what with those?
Add them all together.
Add them all together, right? I'm going to add all those together, and that all those little bits of changes in height will give me the accumulated height or the height of the basketball at 5.5 seconds. Okay, so we just add them up. And then you guys want to use sigma notation? What would it be?
I is 1.
I equals 1 to
11.
11 of V I delta x. So we could say that's like H11. And that 11 corresponds to 5.5 seconds. Okay, let me just talk about the homework. The homework is posted, and the quiz is posted, but the homework for Wednesday, it's a little bit longer, so please start tonight. It's really important that you dig into this homework tonight, because we're doing the hard stuff now, okay? Longer homework for Wednesday. Get started early.
Here's the
Homework?
I have a question for the graphic calculator, the piecewise function. Is that I didn't define the function.
Right.
I don't know how to define the function.
That's
Is that BP1 x plus R1
Let me
x
turn off the
plus
video.